Periodic battery testing helps determine when and what kind of maintenance a battery needs. It helps verify the physical condition of a battery, its state of charge, and its ability to operate when needed. This first part of the program will look at voltage and resistance testing. The key points that will be covered include the purpose of and basic steps for checking cell voltages and intercell connection resistances. We'll start with the cell voltage tests. A cell voltage test is one way to determine if each cell in a battery is being adequately and uniformly charged. IEEE Standard 450 recommends checking pilot cell voltage once a month and all cell voltages at least once per quarter. IEEE stands for the Institute of Electrical and Electronics Engineers. Standards established by the IEEE are completely voluntary, although they're universally accepted and applied. Standard 450 also recommends that cell voltages should be checked with the battery charger in the float charge mode. The voltages are tested using an accurate calibrated voltmeter, such as this digital volt ohm meter. The volt ohm meter is set to the DC volt position. The meter used here automatically selects the appropriate voltage range. These cells are lead calcium, and on float charge should test at about 2.2 volts. The voltage is read to the hundredths of a volt and recorded. As usual, all required safety precautions should be observed. Since voltage testing involves contacting cell terminals, extra care should be taken to not short across terminals. The recorded cell voltages can be evaluated in several ways to identify possible problems. One way is to identify the highest and lowest cell voltages and determine the difference between them. The difference is compared to high and low cell voltage differences from previous tests. If there's a noticeable increase in the differences, an equalizing charge may be needed to raise the voltage of the weaker cells. Another way to evaluate cell voltages is to determine the average cell voltage. Then each cell voltage is compared to the average. Any cell that's below the average by a specified amount should be noted. The acceptable variation from the average is typically specified by manufacturer or company standards. Here, any cell that's 5/100ths of a volt or more below the average will be noted. A third way to evaluate cell voltages is to compare them to a critical voltage. IEEE Standard 450 states that prolonged operation of cells below 2.13 volts can reduce the life of the cells. IEEE Standard 450 also states that a cell voltage of 2.07 volts or below indicates internal cell problems and that the cell may need to be replaced. Low cell voltages by themselves do not necessarily indicate a problem with the cells. They do indicate that the cells have been insufficiently charged, which can happen for a number of reasons. For example, a low float voltage setting may not provide adequate charging current for slightly weaker but still good cells. Cell voltages can also be low because of higher than normal electrolyte temperatures. Higher temperatures increase the internal discharge of a cell and result in lower cell voltage. Higher than normal temperatures may be caused by internal shorting. If this is the case, the cell should be replaced. But higher cell temperature is often caused by outside sources, such as direct sunlight and space heaters. Steps should be taken to minimize the effect of outside sources. Another cause of low cell voltages may be poor intercell connections. Poor connections increase resistance and reduce current flow in the battery. With reduced current flow, weaker cells may not become fully charged and, as a result, will have lower voltages. The resistance from a poor connection can also cause heating. Excessive heating of high resistance connections can melt the terminals. In extreme cases, poor connections can cause battery fires that destroy the battery and threaten the loss of the substation. Poor intercell connections are sometimes evident by visible corrosion at the terminals. But a terminal connection can look good and still not be good. One way to check the connection is with resistance testing. Connection resistance is commonly measured using a micro-ohm meter. A recommended practice is to connect one probe of the micro-ohm meter to the positive terminal of a cell and the other probe to the negative terminal of the adjacent cell. This micro-ohm meter applies a 25 amp test current across the intercell connector and electronically calculates the resistance. It's a good practice to start taking resistance readings at one end of the battery and work toward the other end. Each micro-ohm resistance reading is recorded. Normal resistances can vary with the size of the battery. According to IEEE standard 484, a resistance reading for a new installation is suspect if the connection has a resistance that's 10% or 5 microohms higher than the average resistance for each type of connection. An example of a type of connection is all intercell connections. Another type is all inter-tier connections. For existing batteries, a connection is suspect if its resistance is 20% higher than the average that was established when the battery was first installed and tested. Or a connection is suspect if its resistance exceeds a manufacturer or company recommended limit. Intercell connections with unacceptable resistance should be cleaned, tightened, and retested. If the resistance is still unacceptable, the cell might need to be disconnected from the battery so that the connections can be disassembled and given a more thorough cleaning. As shown in this part of the program, intercell connection resistance testing helps identify poor connections. Voltage testing was shown to help identify cells that aren't being adequately charged. This part of the program also showed a number of possible causes of low voltages and high resistances. Voltage and resistance tests are two of several tests that are helpful in checking the condition of substation batteries. Another useful test is a specific gravity test. Specific gravity testing will be described in the next part of this program. But before continuing, stop the tape and read the voltage and resistance testing portion of your text and answer the questions provided. The term specific gravity for a substation battery cell refers to the density of the electrolyte in the cell in relation to the density of water. A cell's specific gravity is normally an indication of its state of charge. This part of the program will look at specific gravity testing of substation battery cells. The key points that will be addressed include the purpose of checking cell-specific gravity, the basic steps for checking cell-specific gravity, and the effect of electrolyte temperature on the specific gravity of a cell. As you may know, the electrolyte in a cell is composed of sulfuric acid and water, and the specific gravity of a charged lead-acid cell is typically around 1.210. You may also know that as a cell discharges, the specific gravity of the electrolyte decreases because sulfuric acid leaves the electrolyte and combines with the lead in the plates. As the cell is recharged, the specific gravity increases because the sulfuric acid is driven off the plates and back into the electrolyte. So, specific gravity testing is a useful tool for determining the state of charge of a cell. Specific gravity is measured using an instrument called a hydrometer syringe. Most hydrometer syringes have the same basic parts. At one end is a rubber nozzle that's inserted into the cell. At the other end is a rubber squeeze bulb for drawing electrolyte into the body of the hydrometer. The body is a glass barrel. Inside the barrel is a weighted float with a graduated scale. The scale markings indicate values of specific gravity. In this example, the scale is marked off in increments of 0.002. When specific gravity is checked, all required safety equipment should be worn, and all required safe working practices should be followed to the letter. To measure cell-specific gravity, the syringe nozzle is inserted into the cell. The bulb is squeezed and released to draw a sample into the barrel. Some cells have a sampling tube. If electrolyte is taken from a sampling tube, the first sample is discharged into the vent well. Specific gravity isn't read from the first sample because the electrolyte in the sampling tube doesn't mix with and isn't representative of the rest of the electrolyte in the cell. A second sample is drawn for the specific gravity reading. While a sample is being drawn, the syringe is held vertically so the float doesn't touch the sides of the barrel. Enough electrolyte is drawn to lift the float off the bottom of the barrel, but not so much that the float hits the top of the barrel. If the specific gravity is high, the float will ride high in the sample. If the specific gravity is low, the float will sink lower into the electrolyte. Once the float steadies, the specific gravity is read off the scale at the surface of the electrolyte. The specific gravity reading here is 1.222. This is not necessarily the value that's recorded. Specific gravity is affected by temperature, so the reading may need to be corrected for the temperature of the electrolyte. Electrolyte temperature may be checked using a cell thermometer. Here the cell temperature is 68 degrees Fahrenheit. When electrolyte temperature increases, its specific gravity decreases because warmer liquids are less dense than cooler liquids. When the temperature decreases, the specific gravity increases. The normal or standard reference temperature for electrolyte is 77 degrees Fahrenheit or 25 degrees Celsius. To get an accurate specific gravity reading, the specific gravity is corrected by adding 0.001 to the hydrometer reading for every 3 degrees above 77 degrees Fahrenheit. For every 3 degrees below 77 degrees Fahrenheit, 0.001 is subtracted from the specific gravity reading. Some cell thermometers have a specific gravity correction scale opposite the temperature scale. The correction scale here is marked in thousandths. In this example, the electrolyte temperature is 68 degrees Fahrenheit. The correction factor for this temperature is about -3. So 0.003 is subtracted from the specific gravity reading of 1.222 for a corrected specific gravity of 1.219. This is the value that is recorded for the cell. After the specific gravity reading is taken, the electrolyte is returned to the same cell from which it was taken, and the specific gravity of the next cell can be taken. As with voltage testing, IEEE Standard 450 recommends checking pilot cell specific gravity once a month, and all cell specific gravities at least once per quarter. Specific gravity should be checked before water is added to a cell because the water doesn't immediately mix with the electrolyte. Under normal float charge conditions, it may take 6 to 8 weeks for the water and electrolyte to thoroughly mix. In addition, specific gravity readings should not be taken during or immediately after a battery is given an equalizing charge. The reason is that it takes time for the sulfuric acid from the plates to mix with the electrolyte, so the specific gravity will continue to increase for a period of time after the cells have been fully charged. For this reason, specific gravities should not be checked until the battery has been on normal float charge for at least 72 hours after an equalizing charge. After cell-specific gravities are corrected for temperature, they can be evaluated in several ways. One way is to identify the highest and lowest cell-specific gravities and determine the difference between them. The difference is compared to high and low cell-specific gravities from previous tests. A noticeable increase in the differences may mean an equalizing charge is needed to raise the specific gravity of the weaker cells. Another way to evaluate cell-specific gravities is to determine the average cell-specific gravity. Each cell-specific gravity is then compared to the average. According to IEEE Standard 450, if any cells fall below the average by 0.010 or more, the battery should be put on an equalizing charge. IEEE Standard 450 also states that an equalizing charge should be given if the average specific gravity of all cells drops more than 0.010 from the average installation value. Finally, it's a good practice to regularly disassemble and wash the hydrometer syringe with soap and water. This helps prevent a buildup of sulfuric acid that can cause small errors in specific gravity readings. Specific gravity tests, if done at the right time and when properly corrected for temperature, give a good indication of the state of charge of the cells in a battery. Now, while specific gravity and voltage tests indicate the state of charge of the cells in a battery, they don't tell you if the battery can deliver the necessary power when it's needed. Two tests that do are the integrity and capacity tests. These two tests will be covered in the next part of this program. For now, stop the tape, read the specific gravity testing portion of your text, and answer the questions provided. Cell voltage and specific gravity tests provide a good indication of the state of charge of a battery, but they don't indicate if the battery is able to deliver the necessary power when needed. Two tests that do are the integrity and capacity tests. This part of the program will look at integrity and capacity testing of substation batteries. The key points that will be covered include the principles of integrity and capacity testing, the purpose of each test, the basic components of a typical test set, and the basic steps for performing the tests. The principle of performing an integrity test is to discharge the battery at a high current for a very short period of time. During this high current discharge, voltage drop is measured across each cell. The purpose of the integrity test is to identify problems in the battery's connections and intercell conductors. Typically, when a substation battery is needed, it must deliver a high momentary current to trip circuit breakers. It's during high discharge currents that problems occur in the battery's connections and intercell conductors. In fact, a large percentage of battery system failures are due to defects in internal connections, terminal post connections, the intercell connectors, and jumpers. These defects show up as higher than normal voltage drops during an integrity test. The principle of performing a capacity test is to discharge the battery at a lower constant current until battery voltage drops to a minimum terminal voltage. The time it takes to discharge the battery to the minimum terminal voltage is compared to the battery's rated discharge time to determine the capacity of the battery. The purpose of the capacity test is to determine if the battery can provide backup power for its rated period of time. Before integrity and capacity testing, several battery checks must be done, including a thorough visual inspection of each cell, specific gravity and float voltage checks of each cell, a check of the battery's terminal float voltage, checking electrolyte temperatures of selected cells, such as every sixth cell, and calculating the average cell electrolyte temperature. It's important to know that an integrity test places a high current stress on all the cells. If a cell is mechanically defective, the stress of an integrity test could cause the cell to explode. For this reason, the visual inspection and other preliminary checks are very important. Another test, called an impedance test, may also be useful in identifying defective cells before an integrity test is done. The impedance test will be shown later in this program. In addition to the preliminary checks, the safest way to conduct an integrity and capacity test is to take the station battery out of service and replace it with an auxiliary battery. If this isn't possible, the station battery must be tested with the system load connected. For this example, a mobile battery in a specially designed battery trailer will provide the backup power for the DC system while the station battery is being tested. To replace the station battery, the mobile battery is connected in parallel with the station battery according to company procedures. Then the station battery is disconnected from the DC system. Next, the test equipment will be connected to the station battery. Setup procedures vary with the equipment that's used. Be sure to follow the specific procedures for your test equipment. Here, test leads from a control unit were connected to the battery. A numbered test lead was placed in numerical order on each cell's positive terminal, starting with the first cell and continuing on to the last cell. With the leads connected in this manner, the control unit will measure the voltage drop for each cell and its intercell connector. Then the control unit was connected to a master load unit. The master load unit is regulated by the control unit to draw the required current from the battery. Both units are plugged into an AC outlet. The load unit has two cables, which are connected to the positive terminal of the first cell and the negative terminal of the last cell. Once the equipment is properly connected, the control unit is programmed for the desired test duration and current. For the integrity test, the test duration is a period long enough to measure the voltage drop across each cell. In this case, 60 seconds. The test current is a value that's as high as the peak current of the normal station load. In this example, 70 amps. For the capacity test, the duration of the test is a period of time that is shorter than the battery's rated discharge time. For example, this battery is rated to deliver 25 amps continuously for 8 hours before discharging to its minimum acceptable voltage. However, the control unit will be programmed for a 3-hour rate of discharge. The test current is determined from the manufacturer's ampere-hour rating of the battery for the selected discharge rate. In this case, the battery should deliver 50 amps continuously for the 3-hour test before discharging to its minimum acceptable voltage. The rated current, 50 amps in this example, is divided by K, which is a correction factor based on the average cell temperature. For example, using this temperature correction chart, if the average cell temperature is 68 degrees Fahrenheit, the correction factor is 1.056. The rated test current of 50 amps divided by the correction factor of 1.056 gives a test current of about 47 amps, which is entered into the control unit for the capacity test. The control unit is also programmed for a variety of alarm and cutoff values. Some of these may include low cell voltage, to sound an alarm if any cell drops to a critical voltage, usually 1.75 volts. Low cell voltage shutdown, to stop the test if any cell voltage drops to a critical voltage at which the cell could reverse its polarity. This is usually 1 volt. Low battery voltage, to sound an alarm if the total battery voltage drops to a critical voltage, usually 1.75 volts times the number of cells, in this case 42 volts. And low battery voltage shutdown, to stop the test if the battery reaches its minimum acceptable value. In this case, the minimum value is 42 volts, the same as for the low battery voltage alarm. Some control units may include a video monitor, which visually indicates the voltage of each cell during the tests. In addition, a printer may be connected to the control unit to provide printouts of cell and battery voltages. If a printer is used, the control unit is programmed to provide a printout at specific times during the test. After the control unit is programmed, the time and date are entered and the tests are started. During the integrity test, a high current is drawn from the battery. This is a critical part of the test. Individual cell voltages must be read and compared against each other. If a cell voltage is 0.03 volts below the average or adjacent cell voltages, the cell should be checked with a digital voltmeter to determine if the excessive voltage drop is caused by the cell or by the intercell connector. Cell voltage is measured across the positive and negative terminals of the cell to exclude the intercell connector. If this voltage is similar to the other cell voltage readings, the excessive voltage drop is caused by the intercell connection. Poor intercell connections can cause heating. For this reason, poor connections need to be closely watched for excessive heating throughout the rest of the test. Intercell connector heating can be checked in a number of ways. In this example, heating is monitored using an infrared camera. When properly used, an infrared camera will show any hot battery connections. These connections will need to be cleaned and checked for high resistance before the battery is put back into service. During an integrity and capacity test, cell voltages typically change in a somewhat predictable pattern. At the start of the integrity test, cell voltages will drop sharply when the load is applied. Then, when the load is reduced for the capacity test, the voltages will recover to a higher level and hold steady for about a third of the total test time. Then the cell voltages will drop steadily through the rest of the test. For the last 20% of the test time, the voltages start to drop faster. If a cell drops to 1.75 volts, the test should be temporarily interrupted. Then the weak cell is disconnected from the battery following the appropriate procedures and bypassed with a jumper. The cell is bypassed because once a cell reaches 1.75 volts, the voltage will drop off quickly. If it drops below 1 volt, the cell may reverse polarity and will be ruined. The low battery voltage value that was programmed into the control unit must then be reduced by 1.75 volts for each bypassed cell, and the test is continued. The time that the test was interrupted is noted so that it can be subtracted from the total test time when battery capacity is calculated. The test is done when the battery reaches its minimum acceptable value, in this case 42 volts, or when the test time expires. Battery capacity is then calculated using this formula. Percent capacity equals TA over TS times 100. TA is the actual time it took for the battery to discharge to the minimum voltage. In this example, 3 hours and 5 minutes, or 185 minutes. TS is the battery's rated time for discharging to the minimum acceptable voltage. In this example, the rated time is 3 hours, or 180 minutes. 185 divided by 180 is 1.03. 1.03 times 100 is 103. So the capacity of the battery is 103%. IEEE Standard 450 recommends that a battery be replaced when its capacity drops below 80%. If the battery passes the capacity test, any high resistance connections that were noted are cleaned and rechecked for resistance using a digital micro-ohm meter. Then the battery is returned to service according to company procedures. Typically, the battery is given an equalizing charge to restore it to full charge. As we saw in this part of the program, integrity testing identifies problems in the battery's connections and intercell conductors, and capacity testing determines the remaining useful life of the battery. Both tests help indicate if the battery can deliver the necessary power when it's needed. However, repeated capacity testing can shorten the life of the battery, so it's only done about every 5 years. Between capacity tests, the remaining life of the battery can be checked with another test called the impedance test. Impedance testing will be described in the next part of this program. At this point, stop the tape, read the integrity and capacity testing portion of your text, and answer the questions provided. Capacity testing is a proven way to determine the remaining useful life of a battery, but excessive capacity testing can shorten the life of the battery. For this reason, capacity testing is only done about every 5 years. Between capacity tests, the remaining life of the battery can be assessed with impedance testing. This last part of the program will describe battery impedance testing. The key points that will be covered include the purpose of battery impedance testing, the components of an impedance test set, the basic steps for performing the test, and evaluating the test results. The purpose of battery impedance testing is to assess cell condition and the remaining life of a battery while the battery stays in service. The value of measuring cell impedances is based on the principle that cell impedances increase as the battery's capacity decreases. This chart shows a typical curve of cell impedance over the life of the cell. During the first year or two, cell impedance varies some and finally settles to a baseline value. Then the impedance slowly rises as the cell ages and the plates sulfate from use. In the final stages of the cell's rated life, cell impedance increases dramatically over a relatively short period of time as the cell rapidly loses capacity. A cell that ages and loses capacity prematurely will show a rapid increase in impedance during the earliest stages of its rated life. As with any other work done on a battery, all the required safety equipment should be worn and all safe working practices should be followed during the impedance testing. In addition, the battery charger should be in the float mode and should be supplying current to the DC loads. The battery should not be discharging. One component of the test set used to measure impedance is the transmitter. The transmitter generates a low-frequency AC current. A second component is the source leads, which are used to apply the AC current from the transmitter to the battery. The transmitter should be switched off when the source lead connections are made. The leads are first connected to the transmitter, and then to the negative terminal on the last cell of the battery, and to the positive terminal on the first cell. After the source leads are connected, the transmitter is plugged into a standard AC outlet and switched on. A third component of the test set is the receiver. Jaws on the receiver are clamped around an inter-cell connector or an inter-tier connector. The receiver then measures the AC current flowing through the battery. Voltage probes connected to the receiver are placed firmly across the terminals of the cell being tested. The receiver then also measures the AC voltage across the cell. The receiver uses the AC current and AC voltage values to internally compute the cell impedance. It then displays the impedance in milliohms. The impedance is recorded on the battery impedance data form provided with the test equipment or on your company's specific test form. The impedance of each cell in the battery is checked in the same manner by simply moving the voltage probes from the terminals of one cell to another. In addition to checking cell impedance, the impedance of intercell connections can also be checked by placing the voltage probes across the terminals of adjacent cells. After the impedance tests are completed, the receiver is removed from the battery and the transmitter is turned off. Then the source leads can be removed from the battery. To avoid the possibility of arcing, the source leads should be removed only after the transmitter has been turned off. The impedance measurements can be interpreted for individual cell condition and for remaining cell life expectancy. To evaluate cell condition, the cell impedances for the entire battery are averaged. Then the individual cell impedances are compared with the average. If cell impedances vary by more than plus or minus 20% from the average, the battery may need to be put on an equalizing charge, or the questionable cells may need to be capacity tested. Each cell impedance can also be charted with previous readings for the cell and compared to the normal cell impedance life curve. If there's a rapid increase in impedance, the cell or the entire battery may need to be replaced, depending on the age of the battery. The same historical comparisons can also be made for the impedances of intercell connections. Connection impedance is similar to connection resistance, although they cannot be directly compared. Connections showing significant increases in impedance may need to be thoroughly cleaned to reduce the impedance. The unfailing operation of a substation battery is crucial to the protection and control of substation equipment and transmission and distribution systems. The tests described in this program help to ensure that the battery is capable of performing its function. The tests described in this program include voltage and resistance testing, specific gravity testing, integrity and capacity testing, and impedance testing. This unit on substation battery testing, together with the units covering substation batteries and substation battery chargers, provide a solid foundation for the maintenance and testing you perform on your substation's batteries and battery chargers. To complete your training in substation battery systems, you may want to continue your training by learning about substation battery, cell, and charger replacement.